So now in this video we're going to come back to the circuit from the last video. We're only going to look at it when we have a short circuit there. So we have this wired as a current source. We limited the current to 10 milliamps of current. We're going to go over to the power supply. You can see we got 13 volts, which I thought was about the maximum voltage we should use based on an earlier video. But we could actually go higher with this. But in any case, you can see it's showing 9 milliamps right there. It's probably about 9.7. This isn't as accurate as a multimeter though. I'm using a 510 ohm resistor instead of a 500 ohm resistor. So we'll zoom in. In any case, with this circuitry we saw in the last video, we get 10 milliamps of current coming out. And we can put LEDs in the way or other loads. It'll hold 10 milliamps as long as they don't limit current even further than that. Ultimately, we need enough supply voltage to power the current setting resistor. So thanks to the transistor and a 5.6 volt zener diode, we're going to have pretty much 5 volts across that resistor no matter what. The rest of the supply voltage is going to go across the transistor. That's how it limits the current from the resistor. And then the load. So whatever, we got 5 volts for the resistor, whatever the load needs, the rest of the voltage will go across the transistor. With no load, that means, it might be kind of hard to see there, I made it in orange, but we got 8 volts across there. We're going to look at that with the multimeter closer to the end of the video. But in any case, we always have 5 volts across that resistor thanks to the transistor. So we don't have to worry about that unless it short circuits or something. We fry the transistor. That may come up. So if you're worried about that, you may have to address that. But for this video, we're just going to assume that it's always 5 volts across that resistor. Things working out well. That's only 0.05 watts because you take the voltage across it times the current flowing through it and you get the watts. So I thought the transistor would be higher. I think I did at one point anyways, but I actually did the math. If we got 5 volts across there, the short there, so no load taking any of the voltage. The rest of the voltage, so 13 minus 5 is 8. So again, we got 0.01 amps, 10 milliamps of current going through. That's only 0.08 watts. And the 2N3906, which I'm using there, or on the board I should say, you could use any PNP bipolar junction transistor for this circuit, pretty much. But in any case, it has a maximum wattage of 0.625 watts. So you should probably keep that below 0.3 watts, but in any case, that's much higher than what we got there of 0.08 watts. So we could actually go up quite a bit in voltage with this. And I wrote short circuit. That's the collector to ground. It's a direct connection when you should have a load. We're just wasting current right now. But this is one way you could protect a circuit from short circuiting, is having a setup like this where you set a maximum current and then the load can lower the current from there. So now when it comes to voltages in circuit, it's good to get used to measuring them. So we got, this is an auto ranging meter. All I have to do is set it to voltage and it does the rest. It automatically sets the range and everything. If you have a meter with the range, make sure you set it to a range that goes higher than what you can expect. So in any case, there you can see, looks like we're losing a little bit of voltage on the way. That's the supply voltage. We got about 12.9 volts. Ultimately, the voltage across the resistor there is set by the zener diode. So we'll see that we got 5.6 volts across that right there. If we look at in relationship to ground, it should be about 5.6 volts less than the 13 volt supply there. But in any case, that transfers over to this resistor, and we will see that we got, looks a little shy from 5 volts. So again, electronics is not perfect numbers. Generally, it is approximations for the most part. And there you can see we got a little less than 8 volts across the transistor, as we saw before. So that's really the most important voltages on there. So I think we will end that right there. And now we're going to do a comparison. So I have a 1000 ohm resistor there. It's actually warmer than it should be, 0.165 watts. But we're going to do a comparison to see how much heat these are creating. So there's my finger there. You can see it's kind of pink looking. And the resistor and the transistor that we were looking at are warmer But there you can see, compared to that resistor, this one's lighting up a whole lot more right there. So it's definitely a lot hotter. We have a lot less wattage, a lot less heat being produced by these two components than that one. It looks better with the looking at the thermal camera in person. You can really see that it's a lot hotter. But hopefully that was still good enough. When it comes to heat and electronics and all kinds of other stuff, those thermal cameras are really great. I think I paid like $350 for it. It's really nice. But any case, that's it for this video. Hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.